Thank you. A second. Just a second. So we'll start now. I hope people will still joining and join. Okay, so we we have completed module 7. Uh, uh, we'll start with module 8 today. There's something going on with the screen. I'm still figuring out with this new stylus that I have. Yeah, this works. So we'll start with some other antenna types today, and we'll cover traveling wave and helical antennas. So if this is the textbook, so we are here. We'll cover two of the antennas type today, and two of them in the next class, and then we'll look at module 9. Okay. So in the previous class, we discussed the um, wave propagation near Earth's surface and the phase transmission formula and the radar equation. I'll share an assignment in a couple of days, maybe two assignments based on the work that we have done in the previous classes. Okay, so we'll start with the next module, some other antenna types. So up till now, we have been focusing on the radiation properties of linear antennas and their current distribution. So, but the practical antennas, they are not always linear antennas, uh, and they come in different shapes and sizes, and each of them is designed for specific desired performances. So, first one is traveling wave antennas. Although I think these were popular, but not not popular now. But we should know how these function and uh, how they are different from the linear antenna. So they are very similar to half wave dipole, but instead of the dipole being arranged above the let's say this is the um, ground. So this is above the half wave dipole is oriented perpendicular to the ground. So then this ground gets basically by using the image theory, you can remove this ground and make a complete dipole. And this is then you do the math. But instead, in this case, we have the ground over here and the dipole is arranged like this. Then and we have the excitation at this end, and we have a terminating impedance over here, which we did not have in the case of dipoles or half-wave dipoles. So in this case, the when the excitation was included in the dipole. Um, the currents were uh, the currents developed, and then we had the standing waves over here, and which were then radiated. In this case, we have a terminating impedance over here. And in the analysis of thin linear antennas, so let's start with text. In the analysis of thin linear antennas, we assume that the center-driven dipole antennas were not terminated, that the currents from the excitation sources were reflected at the ends. So in these cases, we assume that the currents were reflected from the ends, and these contributed to the standing wave distribution. So if an antenna is several wavelengths long and adequately terminated, as illustrated in 1121 over here, so this in this case, the antenna is much is greater than uh, the wavelength lambda, and it's adequately terminated. That is, we have some termination over here. We have a situation similar to that of a transmission line terminated in a characteristic impedance. So what this terminating impedance will match the impedance created by this uh, uh, the structure which resembles a transmission line. So you have one conductor, you have a ground, and then this makes a transmission line system, and then we are terminating it. So since this is matched over here, so this results in that there are no reflections from this end, and the antenna forms a traveling wave. So instead of forming a standing wave, this forms a traveling wave. That's hence the name traveling wave antennas. So let's so this is the expression for the current in the traveling wave antenna. And for now, let us disregard the effects of the ground. So in this case, we can write the far zone electric field of this isolated antenna by this expression. So this is the electric field due to this traveling wave antenna and neglecting the effect of the ground. So in this case, we have the expression for the electric field, and since then substituting the expression for this traveling wave current, uh, we in the electric field, we can get the expression for uh, the electric far zone electric field due to this antenna. So we have so what we did, we had the expression for current over here for the traveling wave. We substituted that current inside the far zone expression for the far zone electric field, and we have got the far zone electric field for the traveling wave. So okay. So, and if once you have solved this, we get the expression this the expression for the uh, pattern distribution over here as this expression, and this is the pattern function for the isolated traveling wave antenna of length L. So this L is greater than lambda. Okay, so we had the expression of the current in the traveling wave antenna. We substituted that in the expression for electric field, solved it to get the electric field for the traveling wave, and we got the expression for the pattern function. Comparing this pattern function uh, with so this is the pattern for the traveling wave antenna, and this is the pattern function for for a standing wave antenna. And if you compare these, they are different. And one of the important differences is that the pattern function for a standing wave antenna is the symmetrical. Yeah. How do I erase this? Okay. Now I'm not sure how to erase. So this is symmetrical, and the pattern function for the isolated traveling wave antenna is asymmetrical. I still can't. So anyways, so this is asymmetrical. I'm sorry for the bad handwriting. I'm still figuring out with this stylus. So that's the difference. So this is for the derivation for the traveling wave antennas. Um, okay, maybe I should pause over here and take any questions if you have. Just to recap, we 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 wrote down the expression for traveling wave antennas, and in the traveling wave antenna we have this terminating impedance over here, and hence we do not have standing waves, we have traveling waves, as there are no reflections from the end. And for this, we have the expression for the current, and then we substitute that in the expression for electric field to solve the electric field and get the expression for the pattern function. And this pattern function, when compared with the standing wave or the dipole antenna, we see that they are not the same. And in this case, the traveling wave antenna and the pattern function for the traveling wave antenna is asymmetrical. This is no longer symmetrical, and this symmetry is with respect to uh, t, uh, theta is equals to pi by 2. Okay, I see there's a question. Uh, are all mathematical equations important? Need to remember in case of designing antennas. Um, I mean, the equations are important, but you don't have to remember them, is what I believe. You always have the textbooks in hand. You should just know how the physics behind them work, like uh, the differences between the traveling wave, or like you should know which type of antenna is needed for what application, and then you can choose the type of antenna, and then always refer the textbook. You don't have to remember the expressions if that's the question. But if the question is, are the mathematical equations important? Yes, because from these expressions, the equations, uh, we get to know how the things are function, but you don't have to remember them. Okay. If any follow-up questions on that, because I don't think. Okay. Uh, any other questions? Well, I do get how I this question would come up, because till now we have gone through so many equations, and I think it's impossible to remember all of them. Uh, but yeah, we do know we what kind of antennas that we discussed. We did dipole antennas. We did uh, electric dipole and magnetic dipole antennas. We did the radiation pattern, the press equations. So we should remember the things that we have gone through, and when needed, we can refer to the text. So there are very good websites like in case you want to look for results. So there is one website known as Microwaves 101. Microwaves 101. And there is then, I think it's everything RF. These are these are really good websites. So if you want to quickly look at some expressions or some definitions, so these websites. So I'm sure I don't remember who hosts the Everything RF, but Micro 101 is hosted by IEEE, IEEE MTT Society, MTTS, Microwave and Technology Society. So you can trust the material if you which you read on the websites. Okay, so we'll continue then. So the typical radiation pattern of an isolated traveling wave antenna that is several wavelengths long may look like this. So if it was a regular dipole antenna, the radiation pattern would be like this. But for a traveling wave antenna, this becomes tilted. And based on the wavelength and frequency, this tilt will change. So in general, the main beam tilts towards the direction of the traveling current wave. So this is the traveling current wave direction, and this is the main beam. So it is instead of being this like vertical like this, it has tilted towards this direction. And the longer the antenna, the more is the tilt. So if this uh, if this was this length, it will be tilted like this. If we increase the length, the tilt will increase like this. And something to be always remember in traveling wave antenna, the side lobe are generally only a few decibels down from the main beam. So this is the first side lobe, and the difference between the side lobe and the main lobe is less. So if you are not if you only want one beam, the traveling wave antennas is not the right choice. But if you want many grating lobes, in this case, this is an excellent choice. And so, in the previous discussion, what we did was we neglected the effect of the ground plane. So let us and so to consider the effects of the ground plane, we'll just use the principle of am I still audible? Please let me know if I get disconnected. So I there was some sound in the system. Okay, thanks. Thanks, Mohammed. So to consider the effects of the ground, we will use the the image theory, and so in this case, we have removed the ground, and now we have included its the image of the antenna over here. So since this is example, so this is the ground is acting like we're using the image theory. And for the PECs, if we have the current flowing in this direction, and so the direction of the current will get reversed in the image. So now if this was the direction of the current over here, the direction of the current in the image is the opposite. And now we have a system system which looks like an array, and then we can take we had and the previous discussion we had the expression for the electric field for the first element. Similarly, we can write the expression for the electric field for the second element, and then we can solve it, or we can use the our previous knowledge of uh, array factor, and then we can directly write the expressions as well. So, by using the principle of pattern multiplication that we saw in the when we solve for the array factor, this is the coefficient that will be added, cos phi and cos pi by 2, and this cos pi by 2 in this case will be cos beta h is the which is this different height of the traveling wave antenna from the ground, uh, beta h sine theta cos pi and pi by 2, and we can simplify this to sine beta h sine theta cos phi. So we don't need to stress about the math. Somebody has already done this for us. We just need to see. We just need to know that uh, we started with the traveling wave antenna where we had the terminating impedance, which is different from the dipole. So instead of having a standing wave, we have a traveling wave. We had the expression for current over here, as this, and from the current we got the expression for electric field. Now, and then we got the pattern function, and now by using the pattern function and the principle of pattern multiplication, we have the we have the uh, we have the array factor, and hence we have the expression for the complete uh, traveling wave antennas. The the expressions for the complete traveling wave antenna system. Okay, so this is all for the traveling wave antennas. Before we start the helical antenna, I'll just pause over here and let you read the slide. And if you have any questions, we can discuss them as well. Okay, so if there are no questions, we'll start with helical antennas. So before we start we with the expressions for helical antennas, we will briefly discuss why we need helical antennas or or circularly polarized antennas in general. So we have seen that the far zone electromagnetic field produced by linear antennas and small loop antennas are linearly polarized. So this we know this because when we derived the expressions, we had either E theta or E phi. Uh, and the electric field at a given location has fixed direction and does not change with time. And yeah, so if you remember and, uh, when we wrote down the far zone electric field for vertical dipole, it turns out to be a theta, e theta, and for horizontal loop, it's a phi, e phi. The and the signals radiated from these antennas can be received efficiently by a linear antenna oriented in that direction. So this means that if an antenna is oriented like this, it can be received by another antenna which has the same orientation. So if it is like this, they will receive each other. So, for example, if it is arranged like this, they will. So basically, if they have similar orientation, they will receive for loop antennas as well. If the loops are arranged in similar fashion, we will have uh, we, they will the transmitted signal from one of the antenna will be received by the other. But if, for example, if we had and dipole antenna arranged like this and the other one arranged like this, in this case, we will have a mismatch and the signal received will be very low. So in this and in these cases, but in but there will be circumstances where we don't know how the antenna is arranged. For example, we just have an antenna with us and we don't know how the transmitting antenna is arranged. So how do we set up our receiving antenna? So in these cases, what we do is instead of using our linearly polarized antenna, what we can do is we can use a circularly polarized antenna. And the circularly polarized antenna will be able to receive waves in any receive waves of any polarization. Or similarly, what we can do is if we know that the receiver has a linearly polarized antenna, what we can do is we can transmit a circularly polarized wave, and the circularly polarized wave, the linear antenna will be able to receive the signal as well. So. So there are circumstances, however, in which the direction of polarization of the incoming radiation is unknown, or the orientation of the receiving antenna changes, such as the antennas on satellites or space vehicles. The other cases, for example, even if you know how the transmitter is arranged, what can happen is the receiver is with you or on like satellites or space vehicles which are floating in space, and their orientation might change. So in those cases, we have to make sure that this reception is still there, and in those cases we use circular polarization. So no reception will occur when the receiving antenna happens to be perpendicular to the direction of polarization of the signal, and so this is for linearly polarized antennas. So this paragraph is on how the Earth communication works and why we need circularly polarized antennas as well. So again, the signals transmitted from the Earth to the satellites in space, they also have to be circularly polarized because we have a layer of ionosphere. And even if this is a geostationary satellite and the position is fixed, and we have the transmitter over here, what will happen is the signals which are transmitted when they transmit through ionosphere, the polarization might change. So in all these circumstances, this circularly polarized antennas have disadvantages because they are able to intercept waves polarized in any direction and direction not normal to the plane of the circular polarization. So this is why CP antennas are very popular. And how do we get CP circularly polarized waves? What we can do is we can use two equal magnitude linearly polarized waves in both space and time quadrature, and they yield a CP. So what we can do is we can have one antenna oriented like this, the other antenna oriented like this. So they are in space quadrature now, and then when we excite them, we do a phase difference of uh, 90 degrees, and we have quadrature in time as well. So so if you have both space and time quadrature, you get circularly polarized waves. And so and this kind of orientation where you have cross dipole arrangement, it's called a turnstile antenna. What we uh, and in this case where you have two dipole antennas arranged like this and they have a phase difference of 90, but if their magnitude is not equal, in that case instead of having a circularly polarized wave, you will have an elliptically polarized wave. The other way we can do, we can have a circularly or electrically polarized wave is we have a electric dipole and a magnetic dipole, and their arrangement can also give us uh, their arrangement can also give us circularly polarized waves. So, so this is one of the ways. We have cross dipoles, we have uh, electric and magnetic dipoles, and now we have something called as helical antenna, which can give us circularly polarized waves. Because if you look closely, they do resemble in one of we will see in the coming slides. We have something called as normal modes, normal mode, and then there's an axial mode. So in the normal mode, we see that we can consider this as an array of uh, magnetic dipoles and electric dipoles arranged like this. And so hence this functions as this gives us circularly polarized waves. So let's look at the definition. A helical antenna is a wire antenna wound in form of a helix, very evident over here. It is usually installed over a flat grounded conducting plane. So this is the flat grounded conducting plane. And this is fed by a coaxial transmission line. So this is fed by a coaxial transmission line. So very simple structure. But very complex maths. We'll see that. And depending on the dimensions of the helix, the helical antenna has two quite different modes of operation. So these are the two modes of operation: normal mode and the axial mode. And these depend based on how you have like wound the helix antenna and how is this physical structure. So if they are if they're wound very tightly and they're very small, they act as normal mode, and if they are large and wound loosely, they are axial mode. So I'll pause over here and take any questions that you might have had from the previous slides or from this slide. In in the previous slide and this slide, we looked at why we need circularly polarized waves and circularly polarized antennas, and the definition of helical antennas. Okay. So if there are no questions, we'll continue with the helical antennas. We, uh, we will look at some maths and then the two different modes, and then we'll end the class. So for the normal mode, in the normal mode, the dimensions are very small in comparison to the operating wavelength. So let's say this is wound at some d distance, and then there is this r is the radius. So if this r comma d, if they are very much less than the operating wavelength, uh, its radiation pattern in this case is like of an elemental electric dipole, which looks like this. So if this is a dipole over here, we have the radiation pattern like this. So if the radiation pattern is like this, and if from the top, the helix would look like this. So the radiation pattern resembles the if the radiation pattern resembles the electric dipole for the helical antenna, it is said to be operating in the normal mode. And the maximum radiation occurs in the plane perpendicular to the helix axis. So this is the helix axis, and in this direction, the maximum radiation happens. Yeah. So this is the normal mode where the distance of separation d and this radius r, they are much less than lambda. This resembles the uh, electric dipole, and this is the arrangement that I was talking about. So each turn is uh, replaced by a magnetic dipole, and the center we have an electric dipole. And yeah, so for this particular arrangement, what we can do is we can write the expression for the electric field due to the uh, electric dipole and magnetic dipole and the electric dipole, and together for n turns, uh, this is for n turns we have this n, and then we have added the expression for the electric fields, from the superposition principle. So we have the expression for the electric field for this helical antenna. So this is the expression for electric field for magnetic dipole. This is for the electric dipole. And since we have n of these, we multiply them by n, and we add the from the principle of superposition, we add the electric fields. So this is the expression for the electric field. So I'll pause over here, let you read the expression, and if you have any questions on how we got this expression for electric field. Okay, so if there are no questions, uh, we wrote down the expression for electric field due to magnetic dipole, due to electric dipole. Did this sum, multiplied them with n due to we have n such elements over here. We got the expression, and we have this n term because we have n of these elements. So we have the theta and phi components, and they are in they and as you can see, they are in space and time quadrature. So we have theta and phi, which implies this space quadrature, and we have this j term over here, which uh, gives us uh, that they are in time quadrature. And to make them circularly polarized, we have to make sure the magnitudes are equal. So this if this if this s is equals to beta pi b square, we will have circularly polarized, or which simplifying b is equals to root over s lambda by 2. You have to make sure that this separation is and the diameter of the loop, they they follow this expression. So if we do this, we we have the expression for the yeah. So in this case, we will have the circularly polarized waves from the helical antenna. But the problem with this configuration is that the normal mode of the helical antenna, these are seldom used because they have low radiation efficiency and low directive gain. So this this has the radiation pattern look the E plane pattern looks like this, right? So they have very low directivity. So the other mode is the axial mode. So I'll quickly complete the axial mode and then stop for questions. So in the axial mode, the the turns are loosely spaced, and the diameter of the loop is also larger in this case. And in case of the axial mode, uh, will we will not be doing any theoretical analysis because it is very difficult for this particular geometry, and the boundary value problem for determining the current distribution along the helix can be solved numerically, and that too in a limited way. So the usual approach is to do some experiments and observe the results. Uh, and so what we do is we can use solvers or experiments, CEM solvers, and computational electromagnetic solvers like HFSS or CST, or we can do experiments like so we can bound the metal and then do measurements and see how the results are, and then optimize the results for the same. So the thing to be noted in this kind of when the helical antenna is in axial mode, that is when these are loosely spaced, the radiation pattern looks like this. So it is a pattern like this. In the So in case of normal mode, it was broadside, and in this case, it's like an end fire sort of thing. So let's not use those terms. So in this case, this is more directive, uh, and this solves our problem of directivity and gain, which was there in the normal mode. So we simply assert that the radiation pattern of axial mode takes the form of main beam in the end fire direction, together with some side lobes. And the radiation in the main beam is elliptically polarized. The axial ratio of the polarization ellipse being dependent on the frequency and various dimensions of the helix. We have this, this radius. So all those things have to be tuned to get circularly polarized or elliptically polarized. The the helical antennas operating in the axial mode have been installed in communications satellites, space vehicles, and earth stations. And the arrays of helical antenna have been used at radio telescope sites. So you might see in Balanis there is some there's where they're using this big helical antennas in one farm. So that is a radio telescope site. This is all for today's class. In the next class, we'll continue with other antenna types. I'll pause over here for if there are questions on helical antennas in normal mode or axial mode. Uh, and if there are no questions, we'll end the class for today. Thanks, Mohammed. So if there are no questions, we'll we'll end for today. Okay, thanks for joining.